Most people imagine the edge of the universe as a wall. A final boundary where space simply stops and something else begins. Maybe a barrier of fire. Maybe an endless black ocean. Maybe some impossible cliff where reality just runs out. I used to imagine it that way too. But the deeper you go into cosmology, the stranger the idea becomes. Because physics doesn't reveal one edge. It reveals several. And none of them are actual walls. There's the edge of what we can see. The edge of what we can ever reach. The edge created by the geometry of space-time itself, and maybe somewhere beyond all of that, an edge separating our universe from something larger we can barely imagine. But every one of those edges hides the same unsettling truth. They are not places. They are relationships. Boundaries defined by light, time, motion, expansion, and the observer standing inside the universe trying to understand it. So stay with me through this, because by the end, the entire idea of the universe having an edge will feel completely different from the way it does now. There are galaxies visible in our telescopes tonight that humanity will never reach, not with better rockets. Not with impossible technology. Not even if civilization survives for trillions of years. Their light is still arriving here, crossing billions of light years to reach our instruments, but anything we send back today will never arrive there. That sentence should bother you. Because if we can see them, instinct says we should eventually be able to reach them. Maybe it takes a long time. Maybe the journey is unimaginably difficult. But surely distance is just distance. Except in cosmology, distance is not the real problem. The universe itself changes while you travel through it. And once you understand that, the question of where the edge of the universe is begins to unravel. When most people picture the edge of the cosmos, they imagine geography. A finish line. A border. Every journey humans have ever taken trained our brains to think that way. Walk far enough, you hit a coast. Sail far enough, you hit another continent. Climb long enough, you reach the summit. So naturally we assume the universe must end somewhere too. But cosmology refuses to cooperate with that intuition. Instead of one edge, the universe gives us multiple horizons layered on top of each other like masks. The first is the observable universe. This is the maximum distance from which light has had enough time to reach us since cosmic history began. The universe itself is about 13.8 billion years old, yet the observable universe stretches roughly 46 billion light-years in every direction. That sounds impossible at first. How can something only 13.8 billion years old have a visible radius more than 3 times larger than that? Because space itself expands. This is one of the most important ideas in all of cosmology. Galaxies are not simply moving through space like bullets through the air. Space itself stretches between them. While light travels across the universe expands beneath it. So by the time ancient photons finally reach us, the galaxies that emitted them are vastly farther away than they were when the journey began. Looking deeper into space is really looking backward through time. The moon appears as it was 1 second ago. The sun appears 8 minutes in the past. Andromeda appears 2.5 million years younger than it is now. The farther away something is, the older the light we receive from it becomes, and at the very limit of visible history sits the oldest light we can directly observe, the cosmic microwave background. This is where the story becomes genuinely strange. For the first 380,000 years after the Big Bang, the universe was opaque. Not empty. Not dark. Opaque. A superheated plasma filled with charged particles and trapped radiation. Photons constantly collided with electrons and could not move freely. The early universe looked less like empty space and more like the inside of a star. Then the cosmos cooled. Electrons combined with protons. Neutral hydrogen formed. And suddenly light could travel freely for the first time. Some of those exact photons are still traveling today. They surround us in every direction as a faint microwave glow spread across the entire sky, For decades, people casually described this radiation as the edge of the visible universe, but that description is misleading. It isn't really an edge at all. It's a timestamp. We are not seeing a wall in space. We are seeing the oldest moment light can currently show us. And this is where the entire concept of an edge begins to collapse. Because that glowing sphere is centered on us. Not because Earth occupies some privileged cosmic position, but because every observer in the universe sees their own observable universe centered around themselves. An astronomer in a galaxy 10 billion light-years away would also see a sphere of ancient microwave radiation surrounding them. There is no universal center. Only observer-centered horizons. The observable universe is not a giant object floating somewhere in space. It is a relationship between an observer, the speed of light, and the age of cosmic history. And hidden inside that observable universe is another boundary. A far crueler one. The observable universe extends roughly 46 billion light-years away, but the cosmic event horizon, the edge of what we can ever influence, sits much closer. About 16 billion light-years away. Anything beyond that distance is already lost to us forever. Not because it disappears. Not because the light stops. But because the expansion of the universe is accelerating. This is where modern cosmology becomes deeply counterintuitive. Galaxies are not exploding outward through empty space. Instead, space-time itself stretches. The farther away something is, the more expanding space exists between us and it, and therefore the faster it appears to recede. At enormous distances, that recession exceeds the speed of light. That does not violate Einstein's relativity because nothing locally moves through space faster than light. Space itself expands, and eventually the expansion becomes so strong that light emitted beyond a certain distance can never overcome the growing gap. Photons still move at light speed locally. But the space they must cross expands even faster. So the signal never arrives. That boundary is the cosmic event horizon. And this is the part that truly unsettles people once they sit with it long enough. There are galaxies visible in our sky tonight whose present state we will never know. We see ancient light that left them billions of years ago, when they were closer. But what those galaxies are doing right now, at this exact moment, is forever inaccessible to us. If intelligent civilizations exist there and broadcast signals tonight, humanity will never receive them. Ever. The geometry of space-time itself prevents the connection. And the universe gives no visual warning when this happens. Galaxies crossing the event horizon do not suddenly vanish. They remain visible for billions of years because older photons are still arriving. It's like watching delayed footage continue streaming long after the actual connection has already died. The image survives. The relationship does not. That might be the deepest theme in this entire story. The universe allows us to witness events we can never participate in. Over unimaginable stretches of time, those distant galaxies slowly fade. Their light stretches into longer wavelengths through redshift until eventually it becomes too weak to detect at all. One by one, the universe disappears from view. Future civilizations may never even discover the Big Bang. In roughly 100 billion years, distant galaxies will likely have faded beyond detectability. Observers inside the future merged remnant of the Milky Way and Andromeda could look out into darkness and conclude the universe consists of only one isolated galaxy surrounded by eternal emptiness. The evidence of cosmic expansion itself may become impossible to observe. That means we happen to exist during a rare era of cosmic history when the universe is still legible. We are early enough to see the evidence. And the universe is slowly taking that evidence away. Naturally, people ask whether there's any escape from this. Could advanced civilization somehow outrun cosmic expansion itself? That question leads directly into one of the most famous ideas in theoretical physics, warp drives. The idea sounds like science fiction, but it actually emerges from Einstein's equations. Instead of moving through space faster than light, a spacecraft could theoretically distort spacetime itself, compressing space ahead and expanding space behind. The ship would ride a wave of warp geometry. Locally, nothing inside the ship would break relativity because the ship itself would not be moving through space faster than light. Space would move. The mathematics behind this idea became famous through the Alcubierre metric proposed in 1994. And for decades the concept looked impossible because it required enormous amounts of exotic negative energy, but later theoretical work suggested modified versions might reduce those requirements dramatically. Still, even if warp drives someday become possible, they do not actually solve the deeper problem. Because horizons are not merely speed limits. They are observer-dependent boundaries built into space-time itself. Move somewhere else, and a new horizon forms around you. The edge follows the observer. That may be the single strangest realization in modern cosmology. The universe does not have one single edge waiting somewhere out there in the darkness. Every observer carries their own cosmic horizon with them. Their own visible universe. Their own reachable universe. The edge is personal. And once you realize that, the question changes completely. The real mystery is no longer, where does the universe end? The real mystery becomes, why does reality allow observers to experience only limited causal pockets at all? Why should existence be divided into regions that can never communicate? Why should most of the cosmos remain permanently unreachable? And then the story becomes even stranger. Because physicists still do not fully understand what drives the accelerating expansion of the universe. We call it dark energy, but that name is really just a label for ignorance. We know something is causing expansion to accelerate. We can measure its effects. But what it actually is remains unknown. Some theories describe it as vacuum energy, energy inherent to empty space itself. Others suggest entirely new physics beyond our current understanding. And depending on what dark energy truly is, the future of the universe changes dramatically. If dark energy remains constant, the cosmos slowly fades into isolation and darkness over unimaginable stretches of time. But if dark energy grows stronger over time, something even more terrifying becomes possible. A scenario called the Big Rip. In this model, expansion eventually becomes so powerful that galaxies are torn apart. Then solar systems. Then planets. Then atoms themselves. Space expands so violently that reality literally rips apart at every scale. Right now there's no strong evidence this will happen, but the possibility exists within the equations. Which means even the future stability of spacetime itself remains uncertain. And beyond all these horizons lies another possibility. What if our universe is only one region inside something larger? Modern inflationary cosmology suggests that space may contain countless separate bubble universes constantly forming inside a larger inflating structure. Each bubble could possess different physical laws, different constants of nature, maybe even different dimensions. If that's true, our observable universe is not the whole cosmos at all. It's one tiny pocket inside an unimaginably larger multiverse. And there may truly be boundaries separating one universe from another. Not walls in ordinary space, but transitions between entirely different physical realities. Some physicists even speculate that collisions between bubble universes could leave faint scars in the cosmic microwave background. So far, no convincing evidence has been found. But the possibility remains open. And if there are other universes beyond ours, then the phrase, edge of the universe, becomes almost meaningless because our universe itself may only be a small region inside a much larger structure. At that point, the human mind starts running into its own limits. Because every time we think we've reached the boundary of reality, physics reveals another layer beyond it. First, the Earth wasn't the center. Then the Sun wasn't the center. Then the Milky Way wasn't the whole universe. Then the observable universe wasn't the entire cosmos. Every edge dissolves into something larger. And maybe that's the deepest pattern of all. The universe keeps teaching us that boundaries are often artifacts of perspective. The horizon is not an object sitting somewhere far away. It is the limit created by your position inside spacetime. That's why two observers in different galaxies carry different horizons with them. Different visible universes. Different reachable futures. Reality is not experienced globally. It is experienced locally. Every conscious observer lives inside their own causal bubble carved out by light and time. And no matter how advanced technology becomes, that truth remains. You can build bigger telescopes, faster spacecraft, even theoretical warp drives. But you never escape horizons, because the horizon is not a wall waiting somewhere ahead of you. The horizon is woven into the structure of existence itself. And maybe that's the final twist in this entire story. The edge of the universe is not really out there. It is wrapped around you. Right now. Invisible, silent, and constantly changing with every passing second. Not a destination. A condition. Not a place you eventually arrive at. A relationship between you and the rest of reality. And the farther cosmology advances, the more the universe resembles something profoundly strange, an ocean of disconnected islands of information, each observer trapped inside their own expanding sphere of causality, watching ancient light arrive from places they can never truly touch. The universe does have edges. Just not the kind we expected. Even after crossing distances that once seemed impossible, the universe still refuses to give you a final wall. The horizon moves with you. It stays centered on you no matter where you go. That is the strange truth hidden beneath every attempt to find the edge of existence. The farther you travel, the more the universe reveals that its boundaries are not fixed structures in space, but limits tied to the observer. So imagine continuing onward anyway. Past every apparent boundary. Past every cosmic horizon. Past the distance that once marked the edge of the visible universe. You finally arrive where the wall was supposed to be. And what do you see? Not darkness. Not a cliff in space. Not the end of reality. You see galaxies. Endless galaxies. Rivers of stars scattered across blackness exactly like the sky you left behind. The universe continues in every direction with no sign that you have reached anything final at all. This is the moment where the original question begins to collapse. The edge you traveled toward was never the edge of the universe itself. It was only the edge of what could be seen from Earth. From Earth, the observable universe forms a sphere around us roughly 46.5 billion light-years in radius. But once you move somewhere else, that sphere recenters itself around your new location. The boundary resets. The universe does not end. Your perspective changes. This is what cosmologists mean when they say horizons are observer-dependent. Every observer carries their own visible universe with them. Every point in space becomes the center of its own observable cosmos. From your new location, the Milky Way itself would appear ancient and distant, a faint smudge of light glowing from billions of years in the past. Meanwhile, observers back home would see your region in exactly the same way. Each observer stands inside a personal sphere defined not by walls, but by light, time, and cosmic expansion. The deeper you go into cosmology, the stranger this becomes. Because the universe itself may not have an edge at all, modern measurements suggest the geometry of space is almost perfectly flat. The curvature parameter known as omega k is so close to zero that on the largest observable scales, the universe behaves like infinite Euclidean space. Parallel lines stay parallel. Triangles add up to 180 degrees. Circles obey the geometry we learn in school. If that flatness is exact, then the universe may extend forever. No boundary. No final surface. No outer shell surrounding reality. Just endless space continuing beyond every horizon. But there are still possibilities hiding in the data. Some measurements of the cosmic microwave background have hinted that the universe could be very slightly closed, curved like the surface of a higher dimensional sphere. In that case, space would still not possess an edge. It would simply loop back on itself, You could travel forever without ever finding a wall. Finite, but unbounded. Other models imagine even stranger topologies, cosmic structures where space wraps around itself like a multidimensional torus. In such a universe, traveling in a perfectly straight line long enough could eventually bring you back to your starting point. Yet even these exotic geometries refuse to produce the thing intuition expects. No matter what shape cosmologists test, the universe does not naturally generate a reachable edge. Again and again, the wall disappears, and if the universe is truly infinite, something even stranger follows. Somewhere unimaginably far away, there may be another version of you. Not metaphorically. Statistically. In an infinite universe governed by the same laws of physics everywhere, arrangements of matter must eventually repeat. Quantum mechanics implies that any finite region of space can only contain a finite number of possible configurations. If space extends infinitely, those configurations must recur somewhere. Another Earth. Another civilization. Another person hearing these exact words. This idea emerges naturally from the mathematics of infinity. It is one of the consequences explored by cosmologists like Max Tegmark in discussions of the Level 1 multiverse. Infinity changes the meaning of uniqueness itself. But even infinity does not eliminate horizons. No matter how large the cosmos becomes, every observer remains trapped inside a finite causal sphere, the region they can ever interact with. This brings us to the most important boundary of all, the cosmic event horizon. Unlike the observable horizon, which marks what we can currently see, the event horizon marks what we can ever influence. Because the universe is expanding faster and faster due to dark energy, there are galaxies so distant that no signal sent today will ever reach them. Space between us and them expands too rapidly. That boundary lies roughly 16 billion light-years away. And it is centered on you. Not symbolically. Physically. At this exact moment, there exists a sphere around your location defining everything you can ever causally affect. Walk across the room, and the sphere moves with you. Fly to another galaxy, and it follows you there too. The universe does not possess one universal edge shared by all observers. Instead, every observer carries their own horizon, a personal boundary defined by the geometry of space-time and the finite speed of light. That is the final inversion. The edge of the universe is not a place somewhere far away. It is the limit surrounding every observer. And over unimaginable stretches of time, that boundary slowly closes in. As cosmic expansion accelerates, more galaxies slip beyond causal reach forever. Trillions of years from now, nearly every galaxy outside the local group will vanish beyond the horizon. Future civilizations may look into the sky and see only a single merged galactic island surrounded by darkness, never realizing that billions of galaxies once filled the cosmos. The observable universe will shrink into loneliness. An island universe. A fading pocket of reachable reality. There are still more speculative ideas. Some physicists propose that our universe exists inside a bubble formed within a much larger multiverse. According to eternal inflation, different bubble universes could contain entirely different laws of physics. Different particles. Different constants. Different forms of reality itself. In that framework, there could exist a genuine boundary separating our universe from another vacuum state. A real cosmic wall. But even there, the pattern repeats. The wall recedes too quickly to ever reach. It behaves not like a destination, but like another horizon. Every path leads back to the same conclusion. The cosmos does not end in a wall. It ends in limits of relationship. The observable horizon defines what you can see. The event horizon defines what you can affect. Geometry defines the shape of space but not an ending. And every one of these boundaries depends on the observer. The universe is not centered on Earth. It is centered on every observer simultaneously. That is why the search for the edge always fails. The edge is not written into space itself. It emerges from the relationship between light, time, causality, and consciousness moving through an expanding cosmos. The boundary was never out there. The boundary was always around you. And that may be the strangest discovery of all. Because the deeper physics goes, the more the universe stops looking like a giant container with an outer shell and starts looking like a network of overlapping personal horizons, billions upon billions of observer-centered realities stitched together inside one enormous cosmic structure. Your universe overlaps with mine. Mine overlaps with someone else's. Every observer carries a different causal sphere. Every observer lives inside a slightly different reachable cosmos. The universe, in the end, may not be defined by where it stops. Two regions of spacetime can become so separated that no future event in one region can ever influence the other. Ever. They no longer share a connected future. This is one of the strangest implications of Einstein's relativity. Reality is not one giant synchronized stage where everything remains mutually accessible. The universe fractures into isolated causal domains. And over trillions upon trillions of years, those domains drift farther into separation. Eventually, almost every galaxy outside our local gravitational group disappears beyond reach forever, not because it explodes. Not because it dies. Because spacetime itself severs the connection. If humanity somehow survived for 1 trillion years and built instruments beyond anything imaginable today, future astronomers would still face an impossible limitation. They could never observe the galaxies already lost beyond the horizon. The information would be gone forever. The observable universe would slowly contract into a tiny island surrounded by darkness. This leads to one of the most haunting realizations in modern cosmology. Most of the universe is already inaccessible. Right now, at this exact second. Even though we can still see ancient light from distant galaxies, their present reality is already causally disconnected from ours. We are watching history, not current existence. The night sky itself is partly an archive of permanently unreachable worlds. And then comes the truly unsettling implication. If enough time passes, even evidence of the larger universe disappears. Imagine a civilization born 100 trillion years from now. By then, almost every galaxy beyond the local group may have redshifted beyond detectability. The cosmic microwave background itself will have stretched into wavelengths so enormous that detecting it becomes nearly impossible. The universe would appear static, dark, empty. That future civilization might never discover the Big Bang at all. They could conclude that reality consists of one isolated galaxy floating eternally in darkness. And they would be wrong. But the evidence needed to correct that mistake would already be gone. Cosmology itself may only be possible during a brief window of cosmic history. Right now. Which means humanity exists during an extraordinarily unusual era. An era when the universe still allows itself to be understood. That realization changes the emotional tone of astronomy entirely. We often think of ourselves as late arrivals to the cosmos. Tiny creatures appearing billions of years after the stars formed. But in another sense, we may be incredibly early. Early enough to still see the structure of the wider universe before expansion erases it. Early enough to detect the cosmic microwave background. Early enough to measure galaxies racing apart. Early enough to reconstruct cosmic history itself. The universe is not becoming more visible with time, it is becoming less visible. The cosmos is slowly hiding its own origins. And this brings us to one of the deepest mysteries in physics. Why does the universe expand at all? For most of human history, people assumed the universe was static. Even Einstein originally resisted expansion. When his equations implied spacetime should either expand or collapse, he introduced the cosmological constant to force the universe into stillness. Later, after Edwin Hubble discovered galaxies moving away from one another, Einstein reportedly called that decision his greatest blunder. But the story became even stranger in the late 1990s. Astronomers discovered that expansion is not slowing down. It is accelerating. Something is pushing the cosmos apart faster over time. We can measure its effects. We can estimate how much of the universe it represents. Shockingly, ordinary matter, stars, planets, gas, galaxies, everything humans have ever seen, makes up only about 5% of the total cosmic energy budget. The rest is dark matter and dark energy. The majority of reality remains invisible and mysterious. Think about that for a moment. Human civilization built its understanding of existence using only the tiny luminous fraction of the cosmos. Most of the universe is hidden from direct observation, and dark energy dominates the future evolution of spacetime itself. If dark energy remains constant, the universe approaches a state cosmologists call heat death. Stars burn out. Black holes evaporate through Hawking radiation over unimaginable stretches of time. Matter decays. Energy spreads thinly across expanding space. Eventually the cosmos becomes cold, dilute, and dark. Not destroyed. Exhausted. A universe where entropy reaches near maximum levels and organized structure becomes extraordinarily rare. This is not an explosion, it is a fading. The slow dimming of reality itself. But some theories predict something worse. The Big Rip. In this scenario, dark energy grows stronger over time. Expansion accelerates more and more violently until eventually gravity cannot hold galaxies together. Then solar systems. Then planets. Then molecules. Then atoms. Space itself expands so aggressively that every structure in the universe tears apart. Imagine the fabric of reality stretching without limit until existence itself becomes impossible. Fortunately, current evidence does not strongly support this scenario. But physics has not ruled it out completely. Which means the ultimate fate of the universe remains uncertain. And beyond all these possibilities lies an even larger question. What if our universe is not the only universe? We can measure its effects. We can estimate how much of the universe it represents. Shockingly, ordinary matter, stars, planets, gas, galaxies, everything humans have ever seen, makes up only about 5% of the total cosmic energy budget. The rest is dark matter and dark energy. The majority of reality remains invisible and mysterious. Think about that for a moment. Human civilization built its understanding of existence using only the tiny luminous fraction of the cosmos. Most of the universe is hidden from direct observation, and dark energy dominates the future evolution of spacetime itself. If dark energy remains constant, the universe approaches a state cosmologists call heat death. Stars burn out. Black holes evaporate through Hawking radiation over unimaginable stretches of time. Matter decays. Energy spreads thinly across expanding space. Eventually the cosmos becomes cold, dilute, and dark. Not destroyed. Exhausted. A universe where entropy reaches near maximum levels and organized structure becomes extraordinarily rare. This is not an explosion, it is a fading. The slow dimming of reality itself. But some theories predict something worse. The Big Rip. In this scenario, dark energy grows stronger over time. Expansion accelerates more and more violently until eventually gravity cannot hold galaxies together. Then solar systems. Then planets. Then molecules. Then atoms. Space itself expands so aggressively that every structure in the universe tears apart. Imagine the fabric of reality stretching without limit until existence itself becomes impossible. Fortunately, current evidence does not strongly support this scenario. But physics has not ruled it out completely. Which means the ultimate fate of the universe remains uncertain. And beyond all these possibilities lies an even larger question. What if our universe is not the only universe? Maybe even deeper layers beyond that. And eventually the human mind begins encountering limits of comprehension itself. Because our brains evolved for survival on African plains. Not for visualizing curved spacetime, infinity, quantum fields, or multiversal geometry. We instinctively want reality to behave like landscapes. To have edges, centers, boundaries. But the universe resists those instincts at every scale. Even time becomes unstable under deeper examination. Near black holes, time slows dramatically relative to distant observers. Inside quantum mechanics, particles behave like probability distributions until measurement occurs. Some approaches to quantum gravity even suggest spacetime itself may not be fundamental. Space and time could emerge from deeper informational structures beneath reality. Meaning the stage we call the universe may itself be a secondary phenomenon. At that point, asking for the edge of the universe may become like asking where the edge of a dream exists inside a brain. The question itself may stop making sense, and yet despite all this abstraction, the emotional impact of cosmology remains strangely personal. Because every one of these theories leads back to the observer. To you. Right now. Sitting inside a temporary sphere of visible existence. Your observable universe is unique to your position in spacetime. No one else sees exactly the same cosmic history you do. Photons arriving at your eyes tonight traveled billions of years to reach this exact moment. Some began their journey before Earth even existed. You are literally made from atoms forged in ancient stars, living briefly during one of the only eras when the universe still reveals its history, while surrounded by light emitted from unreachable regions of spacetime. That is not poetry. That is physics. And maybe the strangest part of all is this. The universe never promised accessibility. Humans instinctively believe reality should ultimately be understandable and reachable. But cosmology suggests otherwise. Most of existence may always remain beyond contact, beyond observation, beyond explanation. Not because we failed technologically, because causality itself imposes limits. The speed of light is not merely an engineering obstacle. It is part of the architecture of reality. Horizons are not temporary inconveniences. They are structural features of spacetime. The universe allows islands of connection surrounded by oceans of permanent separation. And yet consciousness still emerged inside one of those islands. Matter learned to observe itself. Tiny biological organisms evolved on a small planet orbiting an average star and began asking questions about the structure of existence itself. That may be the most astonishing fact in the entire cosmos. Not that the universe has horizons, but that something inside those horizons became aware of them, because in the end, the story of the universe's edge is really the story of perspective. Every observer occupies the center of their own observable reality. Every conscious being lives inside a personalized horizon defined by light and time. The cosmos is not organized around locations. It is organized around relationships. And perhaps that is the deepest shift modern cosmology forces upon us. Reality is not a static container filled with objects. It is an evolving network of causal connections, a structure defined not merely by what exists, but by what can influence what. The universe is less like a map and more like an ever-changing web of information flow. And somewhere beyond every horizon, more reality continues unseen. Not hidden behind walls. Hidden behind causality itself. The universe is temporary. Even spacetime may not last forever. And understanding why begins with one of the most important concepts in all of physics. Entropy. Entropy is often described as disorder, but that definition oversimplifies it. A better way to think about entropy is this. Entropy measures how many ways a system can arrange itself while still appearing macroscopically the same. Low entropy systems are highly ordered and specific. High entropy systems are diffuse and statistically random. A shattered glass has higher entropy than an intact one because there are vastly more possible broken arrangements than perfectly assembled ones. And according to the second law of thermodynamics, entropy tends to increase over time. This is why eggs do not spontaneously unscramble. Why smoke spreads through air. Why stars eventually burn out. The arrow of time itself may emerge from entropy increasing. The future is the direction in which disorder grows. Now apply that idea to the entire universe. The early universe after the Big Bang was incredibly hot and dense. But surprisingly, it also possessed extraordinarily low entropy. That fact remains one of the deepest mysteries in cosmology. Why did the universe begin in such an incredibly ordered state? Physicist Roger Penrose famously estimated the odds of the universe beginning with such low entropy as unimaginably tiny. Yet somehow it happened. And because it happened, complexity became possible. Stars formed. Galaxies emerged. Planets cooled. Life appeared. Consciousness evolved, all because the universe began far from thermodynamic equilibrium, but entropy has been increasing ever since. The cosmos is slowly running downhill. Every star that shines converts concentrated energy into diffuse radiation. Every process spreads energy more evenly through space. The universe is gradually using up the conditions that allow structure to exist. And eventually, over unimaginable spans of time, this process leads toward a state called heat death. Despite the dramatic name, heat death is not fiery. It is cold. The term refers to a universe where usable energy has been exhausted. Stars no longer form. Galaxies go dark. Matter decays. Temperature differences disappear. Without gradients in energy, no work can occur. No engines. No chemistry. No metabolism. No life. The cosmos enters a thin, nearly motionless state approaching maximum entropy. To understand how strange this future is, we need to travel far beyond normal human timescales. Right now the universe is about 13.8 billion years old. That sounds enormous. But compared to the lifespan of the cosmos, humanity exists almost at the beginning. The stars we see tonight belong to what astronomers call the stelliferous era, the age of stars. This is the bright chapter of cosmic history. Gas clouds collapse into new suns, galaxies glow. Heavy elements form inside stellar cores. Planets emerge around young stars. Life becomes possible. But this era is temporary. Star formation is already slowing. Galaxies are gradually exhausting the cold gas needed to create new stars. Over the next 100 trillion years, most stars will eventually die. Small red dwarfs, the longest-lived stars in existence, may survive for trillions of years. But even they eventually burn out. When the final stars fade, the stelliferous era ends. Then begins the degenerate era, a universe filled mostly with stellar corpses. White dwarfs. Neutron stars. Black holes. Dead remnants drifting through expanding darkness. Occasionally gravity may still produce rare interactions. White dwarfs colliding. Black holes consuming matter. But the cosmos becomes vastly dimmer. Vast stretches of space descend into permanent night. Imagine looking into the sky billions upon billions of years from now. No bright galaxies. No nebulae. No newborn stars. Only darkness interrupted by scattered dying remnants. And even those remnants do not last forever. Protons themselves may decay. Physicists still do not know whether proton decay actually occurs, but many grand unified theories predict it. If protons are unstable, then ordinary matter possesses an expiration date. Over absurdly long timescales, perhaps 10 superscript 3 years or more, atoms themselves dissolve. Planets disintegrate. Dead stars evaporate into elementary particles and radiation. Matter slowly disappears from the universe. If proton decay occurs, almost everything familiar eventually vanishes. But black holes survive longer than anything else. Far longer. For decades physicists believed black holes lasted forever. Then Stephen Hawking changed everything. By combining quantum mechanics with general relativity, Hawking discovered that black holes are not completely black. Quantum effects near the event horizon allow them to emit tiny amounts of radiation. Today, this phenomenon is called Hawking radiation. The process is unbelievably slow for large black holes. A stellar black hole may take around 10 years to evaporate. Supermassive black holes at galactic centers may survive for 10^1 years or more. That number is almost impossible for the human mind to process. A googol years, a 1 followed by 100 zeros. Yet even black holes eventually disappear. Over incomprehensible spans of time, they slowly lose mass through radiation until finally evaporating completely. And when the last black holes vanish, the universe enters what may be its final stage. The dark era. A cosmos containing mostly low-energy photons, neutrinos, and scattered particles drifting through nearly empty space. No stars. No planets. No galaxies. No structure. Only thin radiation spread across eternally expanding darkness. If heat death is correct, this may be the ultimate fate of the universe. Not destruction. Dissolution. The gradual fading of organized existence into thermodynamic equilibrium. But physicists are not fully satisfied with this picture, because quantum mechanics introduces disturbing possibilities even in dead universes. One of those possibilities is the Boltzmann brane problem. In an infinite or eternally existing universe, random fluctuations can occasionally create ordered structures by pure chance. Usually these fluctuations are tiny. But given enough time, larger fluctuations become statistically inevitable. That means an entire self-aware brain with false memories could theoretically fluctuate into existence briefly out of chaos. A Boltzmann brane. The horrifying implication is this: if the universe lasts forever, random observer fluctuations may eventually outnumber naturally evolved conscious beings. Which leads to a deeply unsettling philosophical question. If random observers vastly outnumber ordinary observers, why are we not one of them? Some cosmologists treat this as evidence that certain models of eternal universes must be wrong. Others argue the paradox reveals limits in how probability works cosmologically. But either way, the existence of the problem shows how strange modern physics becomes once infinite time enters the equations. And then there are cyclic universe models. Some theories propose that the universe does not end permanently at all. Instead, cosmic history repeats. A big crunch could collapse spacetime back into extreme density before triggering another expansion. Other models suggest endless cosmic bounces. Yet strangely, consciousness may still be extraordinarily rare. Not central geographically, but precious statistically. If the universe is defined by horizons, expansion, and the gradual separation of everything from everything else, then eventually the question becomes personal. What happens to us? Not just humanity. Not just Earth. But the entire chain of structures we belong to. The planet. The solar system. The Milky Way. Our local region of the cosmos. Because when people hear about the death of the universe, it often sounds impossibly distant and abstract. Something disconnected from human reality. But cosmology becomes far more unsettling when you realize the destruction begins locally. Long before the universe itself fades into darkness, Earth disappears. The sun changes. Galaxies collide. Stars die. Black holes dominate the future sky. A temporary pocket of awareness inside an otherwise indifferent universe. And perhaps that is why cosmology feels emotionally overwhelming, because it forces two truths together simultaneously. We are unimaginably small. And unimaginably significant. Small physically. Significant because matter became conscious here. Atoms learned to think here. The universe produced beings capable of asking what the universe is. And maybe that is the closest thing reality has to meaning. Not permanence. Not destiny. Awareness. The brief flowering of consciousness inside a temporary window of cosmic history. Because eventually, one way or another, the stars go out. Galaxies fade, horizons close. Black holes evaporate. The observable universe dissolves into darkness. Every civilization ends. Every memory disappears. Every structure falls apart. Even space-time itself may eventually transform into something unrecognizable. But for a brief moment in cosmic history, the universe woke up and realized it was alive. And eventually the sun enters the next stage of stellar evolution. In roughly 5 billion years, hydrogen fusion in the sun's core will largely end. Gravity compresses the core. Temperatures rise dramatically. Outer layers expand outward. The sun transforms into a red giant. At that point, the inner solar system changes catastrophically. Mercury almost certainly disappears. Venus likely follows. Earth's fate remains slightly uncertain because the sun will lose mass while expanding, which could push Earth outward somewhat. But even if Earth physically survives the expansion, the planet's surface will already have been sterilized long before. Oceans gone. Atmosphere destroyed. Rock melted beneath an enormous red sky. The world where humanity evolved ceases to exist. And for a brief period, the outer solar system becomes warmer. Moons currently frozen beneath ice, Europa, Enceladus, Titan, may temporarily possess liquid water environments on their surfaces. The habitable zone moves outward as the sun swells. Then comes the final collapse. The sun sheds its outer layers into space, forming a planetary nebula, an expanding shell of glowing gas. At the center remains a white dwarf. A stellar corpse roughly the size of Earth but containing about half the sun's original mass. No fusion. No sunlight, just residual heat slowly radiating away over trillions of years. The solar system becomes dark. Planets continue orbiting a dead star. If anything survives there by then, it would witness one of the strangest skies imaginable. No blue daylight. No warm sun, only a tiny brilliant white ember hanging in blackness, but the story does not stop with the sun. Because while stars evolve, galaxies evolve too. And the Milky Way is moving. Right now our galaxy and the Andromeda galaxy are rushing toward one another at roughly 110 kilometers per second. And eventually even the Milky Way itself transforms into something almost unrecognizable. To understand the true future of the cosmos, we have to start with where we are now. Earth exists inside a very temporary moment. Right now the universe is roughly 13.8 billion years old. The sun formed about 4.6 billion years ago from the collapse of a molecular cloud enriched by older exploded stars. Earth formed shortly afterward from debris orbiting the young sun. Everything alive today exists because earlier generations of stars lived and died before our solar system existed. The iron in your blood. The oxygen you breathe. The calcium in your bones. Almost every heavy element on Earth was forged inside ancient stars or supernova explosions long before humanity appeared. You are literally built from stellar remnants. And the sun itself is not permanent. Right now it is a middle-aged main sequence star quietly converting hydrogen into helium through nuclear fusion in its core. Every second, the sun fuses around 600 million tons of hydrogen. That reaction produces the energy supporting life on Earth. But fusion slowly changes the sun over time. As helium accumulates in the core, the sun gradually grows brighter. This is important because people often imagine Earth remaining habitable until the sun becomes a red giant billions of years from now. In reality, Earth may become uninhabitable much earlier. Over the next several hundred million years, increasing solar luminosity will slowly heat the planet. Oceans evaporate, carbon dioxide levels collapse as geological cycles break down. Plant life dies. Complex ecosystems disappear. Long before the sun physically engulfs Earth, our planet may already resemble Venus, hot, dry, and lifeless. Human civilization exists during one of the most stable and biologically favorable periods Earth will ever experience. That stability is temporary. At first that sounds like a collision waiting to destroy everything. But galaxies are mostly empty space. Stars are separated by enormous distances. Direct stellar collisions during the merger will be extremely rare. Instead, gravity reshapes both galaxies over billions of years. About 4 to 5 billion years from now, around the same era the Sun begins dying, the Milky Way and Andromeda start their first major close encounter. The night sky from Earth, if Earth still existed, would become spectacular beyond imagination. Andromeda would swell larger and larger over millions of years. Eventually it would dominate the sky. Tidal gravitational forces would distort both galaxies into enormous streams of stars. The elegant spiral structures of the Milky Way and Andromeda would unravel. Over time the galaxies merge into one enormous elliptical galaxy sometimes nicknamed Milkomeda. This future galaxy may contain trillions of stars. New waves of star formation ignite as gas clouds collide during the merger. For a while, the universe locally becomes brighter again, then gradually the gas needed for new stars runs out. The merged galaxy ages. Star formation slows. The bright era fades. And by then the wider universe looks profoundly different. Because cosmic expansion continues the entire time. Right now, when we look into the night sky, we see countless galaxies beyond the Milky Way. But over the next 100 billion years, most galaxies outside our local group disappear beyond the cosmic event horizon, not because they explode. Not because they stop existing, because the expanding universe stretches spacetime so rapidly that their light can no longer reach us. Future astronomers living inside Milkomeda may look into darkness and conclude their galaxy is the entire universe. The evidence for the Big Bang itself may become undetectable. The cosmic microwave background will have redshifted into wavelengths too enormous to measure easily. Distant galaxies vanish. Expansion becomes invisible locally. Cosmology itself may become impossible. Humanity exists during one of the only periods in cosmic history when the universe still reveals its large-scale structure. That realization is astonishing. We often imagine future civilizations understanding the cosmos better and better forever, but the universe is actually becoming less observable with time. The cosmos slowly hides its own origins. And eventually black holes dominate the future of galaxies. At the center of the Milky Way already sits a supermassive black hole called Sagittarius A star. It contains roughly 4 million times the mass of the Sun. Right now it is relatively quiet. But during the galactic merger, enormous amounts of gas may fall toward the centers of both galaxies. The central black holes eventually spiral toward each other and merge. The resulting black hole could contain hundreds of millions of solar masses. For a time, it may become an active galactic nucleus, one of the brightest phenomena in the universe. Jets of radiation blast outward across intergalactic space. Then eventually even that activity fades. The giant black hole remains. A dark gravitational engine at the center of a slowly aging galaxy. Over trillions of years, stars gradually die or are ejected through gravitational interactions. Galaxies slowly evaporate dynamically. Some stars fall into black holes, others drift into intergalactic darkness forever. Eventually the Milky Way Andromeda remnant becomes sparse and dim. And if proton decay occurs, even dead stars and planets eventually dissolve. Matter itself may not survive forever. The future universe grows increasingly empty. Yet black holes survive almost longer than anything else. This leads to one of the strangest eras of future cosmic history. The black hole era. By then, almost all ordinary astrophysical structures are gone. The universe becomes dominated by black holes drifting through expanding darkness. Some contain stellar masses. Others hold billions or trillions of solar masses. And according to Hawking radiation, even these giants slowly evaporate. Black holes are not eternal. Quantum effects near the event horizon allow them to emit radiation extremely slowly. For enormous black holes, the process takes incomprehensible lengths of time. A supermassive black hole may survive for around 10^1 years before evaporating completely. That number is so huge that normal language almost fails. If every second since the Big Bang were counted individually, it would not even begin approaching such timescales. Yet eventually even black holes disappear. And after that, the universe enters deep darkness. No stars. No galaxies. No planets. Only thin radiation and scattered particles drifting through expanding space. But there is another layer to this story that makes it emotionally overwhelming. Because every stage of cosmic evolution changes what observers can know. Right now humans can reconstruct billions of years of cosmic history because information still reaches us. We see ancient galaxies. We detect relic radiation from the early universe that we measure expansion. But future civilizations may lose access to almost all of this evidence. The observable universe shrinks into isolation. Imagine intelligent beings evolving 1 trillion years from now inside the remains of Milky Way. Their sky would look almost empty. No visible expansion. No external galaxies. No microwave background. They might conclude the universe is static and eternal. Not because they are unintelligent. Because cosmological evidence itself would be gone. The universe changes what can be discovered depending on when observers exist. That is one of the strangest consequences of cosmic evolution. Truth itself becomes historically accessible only during certain eras. And then comes the deepest question of all. What happens to consciousness in a universe like this? Human beings evolved under bright skies filled with stars. Our myths, navigation, religions, calendars, and sciences all emerged beneath visible cosmic structure. The night sky shaped civilization itself. But future intelligent beings may inherit a nearly empty cosmos. No visible galaxies. No evidence of cosmic origin. No connection to the wider universe. A civilization born late enough might never know how vast reality once appeared. That possibility changes the emotional meaning of astronomy. Because cosmology is not just the study of stars and galaxies. It is the study of what existence allows conscious beings to experience. And maybe the most tragic part of cosmic expansion is not the disappearance of galaxies themselves. It is the disappearance of access. The universe slowly removes regions from causal contact. Not merely physically. Informationally, the cosmos becomes fragmented into isolated islands of awareness surrounded by unreachable darkness. Yet despite all this impermanence, something extraordinary happened on Earth. Matter became alive. Life became intelligent. Intelligence began asking questions about the fate of the universe itself. Tiny organisms on a small rocky planet around an ordinary star learned to measure galaxies billions of light years away. The universe became capable of examining its own history through conscious minds. That may be one of the rarest events in all cosmic history. Because most of the universe is hostile to complexity. The early universe was too hot. The far future may be too cold and diffuse. Human civilization exists during a narrow thermodynamic window where stars shine, chemistry works, and information can still flow across immense distances. A brief era between cosmic fire and cosmic darkness. And that makes this moment profoundly unusual. Right now the universe is still visible. Still connected. Still understandable. The galaxies still shine. The cosmic microwave background still surrounds us. The evidence of cosmic origin still crosses space toward Earth. But none of that lasts forever. The universe is not freezing in place. It is evolving continuously toward isolation. Toward separation. Toward horizons closing around every observer. And perhaps that is the deepest emotional truth hidden beneath cosmology. Everything we know exists inside temporary conditions. Earth is temporary. The Sun is temporary. The Milky Way is temporary. Even stars themselves are temporary arrangements of matter resisting entropy for a little while. The cosmos builds structures, then slowly takes them apart again. Yet during that brief interval, consciousness emerges. Observers appear. Questions are asked. Meaning is constructed. And for one fleeting moment in cosmic history, the universe becomes aware of itself beneath the light of living stars. By now the pattern has become impossible to ignore. Nothing in the universe stays the same forever. Not planets. Not stars. Not galaxies. Even the visible structure of the cosmos slowly dissolves with time, and once you truly understand that, another question naturally appears. If Earth is temporary, could humanity survive beyond it? We are temporary beings living inside a temporary cosmic era, yet capable of understanding things vastly larger and older than ourselves. And maybe that is enough. Maybe existence never required permanence to matter. Maybe the fact that consciousness appeared at all is already extraordinary beyond words. Because the universe did not need to produce observers. Stars could have burned for trillions of years in total darkness with no minds ever emerging to witness them. Instead, somewhere inside the Milky Way, matter learned to ask questions, and the questions continue. What existed before the Big Bang? What is dark energy? Do other universes exist? Is space-time fundamental? Are we alone? Modern cosmology still cannot answer these fully. The edge of understanding remains. But history suggests something hopeful. Every time humanity believed it reached the limits of reality, another layer of mystery appeared beyond it. The horizon kept moving. And perhaps that endless unfolding is the real nature of the cosmos. Not a universe with final answers waiting at the edge, but a universe where every discovery opens deeper questions. An infinite chain of horizons receding forever. And maybe that is fitting. Because the search itself may matter as much as the destination, the desire to understand, the refusal to stop asking, the drive to look upward into darkness and wonder what lies beyond. That impulse carried humanity from caves to telescopes, from myths to relativity, from naked-eye stargazing to measuring radiation left over from the birth of the universe itself. The cosmos remains vast, indifferent, and mysterious. But within that vastness, consciousness emerged. Awareness emerged. Meaning emerged. And for a brief moment beneath the stars, the universe became capable of knowing that it exists. That is where we are now, standing between the past and the future. Between ancient starlight and approaching horizons. Between cosmic beginnings and cosmic endings. Alive during the short era when the universe still reveals itself. Looking outward into darkness while carrying pieces of dead stars inside our bodies. Asking questions no other known part of the cosmos can ask. And somewhere beyond every visible horizon, the universe continues. Silent. Expanding. Unfinished. Waiting for whatever comes next.